Hi, this is the first video about forces, and in this video we're going to look at how you can correctly draw forces onto force diagrams. If you can't draw on all the forces in the correct directions, then you're just going to score 0 marks in any kind of question in mechanics. So it is very important that you do this and you get it correct. And if you're anything like me, you have a phys teacher, they often assume you just get forces intuitively and you just know which direction they go and where to draw them. In this video, we're going to talk about actual rules and guidelines you can follow to try and make sure you never miss a force and you always get in the right direction. So, hope that should give you some certainty and help you out. We're going to look at 4 different kinds of forces. These are the 4 forces that you might have to add on to the diagram yourself. They're reaction, weight, tension, and friction. I have an acronym to help me try to remember these so I don't forget one. The acronym is really what the force is. And we're going to use that to make sure we don't miss a force out. We're going to talk about a few things to do with them. The most important two are these two. When does a force occur and which direction do I draw the arrow in? Most important for drawing a force diagram. We'll also discuss a bit about the formulas and the magnitudes, but we'll deal with those much more detailed in a future video where we try and solve and create equations. Today is about just getting the forces right in the first place. Let's do it from easiest to hardest. So we'll start with weight. Weight is a nice little simple formula here for how big it is. It's just mass times gravity. Gravity here is the gravitational field strength, and it's approximately 9.8 on the surface of the Earth, pretty much everywhere. So they use that in the NXN exam, the AQA exam. So 9.8 is the figure you're going to use there. Times by the mass gives you your weight. The direction, more importantly for us today, is vertically downwards, means straight down. It doesn't matter what angle the object's sitting on, the surface is inclined, the weight force is always going vertically downwards. I have seen some interesting changes of angle, but always straight down. Happens whenever an object has a mass, which is pretty much every object you're going to see. So those objects will have a weight. By the way, things without weight and without mass are referred to as light. But we'll mention that again in the future when it becomes important. Next forces we'll look at, reaction and friction. We'll talk about this together because they often arise together. Reaction and friction will occur when you're touching a surface. A surface could be a wall, could be a floor, could be some kind of plane that's inclined. Whenever you're touching a surface, the reaction force is always perpendicular to that surface. So if this is my floor, then the reaction will be pointing straight up. As I incline it to make it an inclined plane, the reaction is now pointing straight away, perpendicular to it. If it's a wall, it's pointing out perpendicular to the wall. It's always perpendicular. So to help you draw that on, if you're not very good at drawing perpendiculars, and in my experience, some students are just really dodgy with their 90-degree angles, it's okay. I would get a ruler or something with a 90-degree angle. I've got a little whiteboard here, and when I'm trying to draw on perpendiculars, I'll line it up with the surface and make sure that it becomes perpendicular. I'll show you that more when we do some examples in a moment. Friction occurs if that surface you're dealing with is rough. Smooth would mean no friction. Rough means there is friction. The friction, unlike the reaction, is going to be parallel to that surface. As that surface moves, the friction is always going along that surface. And it always acts to try to oppose or resist any kind of movement. Obviously, as you try to rub across friction, friction tries to slow you down, not speed you up. So we'll see like this opposite effect. We'll do that as we see situations, and we'll try and draw on opposite each time. Friction can be tricky, and this direction bit can be really subtle, but we'll do that as we see those scenarios, try to help make sure you understand that well. There is a magnitude for friction. There's a formula for it. Friction is less than equal to mu times r. Mu here is the coefficient of friction. So it's not friction itself, it's the coefficient of friction, it's just a number. Mu is a Greek letter. Mu looks a bit like an M, looks a bit like a U, probably my favorite Greek letter. The coefficient of friction tells you how rough that surface is. So mu is always going to be greater than or equal to 0. If mu were 0, that would mean that there was no friction, it would be a smooth surface. As mu gets bigger, the amount of friction you can generate gets bigger. So essentially, the surface gets more rough, it has a bigger mu value, and that means there's more friction on that particular surface. R here is the reaction force. That's why we talk about them together because they often affect each other. The bigger that reaction force, the more those two things are being pushed into one another, the bigger the friction force can be. The more you push down to the surface, the more you can generate more friction. We'll talk about that more in the future. For now, let's not worry about too much. We just care about the direction, and when it occurs, it's going to help me to make sure that I can get it on my diagram correct. And then finally, tension. So tension occurs whenever you have a string or a cable or a rod or something of that nature, and the string, cable, or rod will be pulling the object. So it acts along the string and away from the object. So imagine if I took a rope and sort of lassoed you, and then I was pulling, that would make sense. I could pull you towards me, but if I lassoed you and tried to push you away from me, and then the rope went slack, you would look at me like I was stranger than you already think I am. So you can pull, you can't push. So along the string and away from the object. Let's look at 3 classic situations and add the forces to them so we can sort of see how this works. And if you still want to see more, I've got a whole other video dealing with like loads of more situations that occurs. So first, we're going to look at, importantly here, just the objects with a letter. So A, B, C, D. We care about the forces on those objects, not about every single force in the entire world, right? So we don't care about forces that are, to do with the pulley or forces to do with the ceiling, just forces on the objects that we're interested in. Let's do A first of all. Really what the forces. So reaction, well, there's a surface, yes, so there's going to be a reaction. It's rough, so there'll be a friction. The reaction is perpendicular to the surface. So take my whiteboard, line up the bottom with the surface. The perpendicular goes this way. All the forces start from the object because they're acting on that object. So reaction pointing away from A, with a dot here, so it's going from A. Friction, well, in this situation, I think this is going to be a string, and as B sort of let go, B will be falling and A will be rising. So let's add a direction here. A is going to be moving upwards. The question would have the word tell us that A is going upwards. So if it's going upwards, that means friction is going to be going against it and going down the plane, again parallel to it. Weight, yes, going straight down, there'll be a weight. Let's call it WA, the weight of A. And then tension, tension's going to go along the string and away from the object. So along the string, pointing away from the object. B next, really what the force is. Well, B has no reaction or friction because B isn't touching a surface. It's hanging in the middle of the air. It's maybe falling, but it's not touching a surface. So no reaction, no friction because there's no surface. Weight, yes, weight is going vertically downwards, so weight of B going vertically downwards. And then finally tension. Well, there's a string touching B, so yes, there'll be a tension force going away along the string and away from the object. These two tensions are the same string, and they're pretty smooth, so there'll be the same tension. We'll talk more about why that's the case when we look at like connected particles in the future, but for now we care about the fact there's a tension force and it's going upwards. C next. So we don't care about forces in the ceiling, just the forces on C. Really what the forces. No reaction, no friction. There's a surface, but it's not touching C. C is not touching the surface, so no reaction, no friction. Weight, going straight down, there's a weight of C. Tension, yes, in fact there's 2, because there's 2 strings, right? One along this string away from the object, one along this string away from the object. Because they're 2 different strings, I'm going to call them 2 different tensions, T1 and T2. They don't need to be the same size force here, right? They could be different amounts perhaps. So I'll call them T1 and T2 now, as we know more. Finally, D here, something resting on a surface, not moving this time. Let's do again, really what the force is. Reaction, yes. Friction, yes, because it's a rough surface. The reaction will be going perpendicular to the surface. Again, mark on perpendicular using a ruler or something. Make sure you get nice and perpendicular. The friction, well, which way is D going to move? D is sitting still, perhaps. It's like sitting there resting. But if you've experienced much of life, if you put something on a surface, it'll either stay still, right, or it'll slide down. So if it's staying still, it must be because the friction is stopping it from sliding down. So the friction is opposing the way it would try to go, and so the friction will be going upwards to try and stop it from sliding down. And apparently, in this situation, the friction is large enough to keep it still. If the friction wasn't big enough, I guess it would slide down. Right? Weight, yeah, D as a weight, vertically downwards. Tension, there's no string in this question, so no tension. There we go. We've added forces to our diagrams. Now we can get on and try to resolve them, create equations, uh, solve equations, find some numbers out. But that's all to come in future videos. If you want more examples, again, next video in this list is more of these examples and look at some exam questions to make sure that you know what you're doing before you try to do the mathsy bit. Okay, check it out.